So we start with one random variable, then we talked about two random variables, and now we're going to start talking about a large number of random variables, a sequence of random variables. So today we're going to focus on what happens if we add up a whole bunch of random variables, okay? Not just one or two, but lots of them, right? So the idea is that we have a set of xi, and each of these has a corresponding PDF, okay? So let's think about this notation. Sn, I'm going to say, is the sum of n of these random variables. And mn is what I'm going to get if I take the average of these random variables. Okay, so what I want to talk about today is, we can think about these as random variables themselves, right? So they should have a mean and a variance and a PDF. But today, in this lesson, I'm just going to focus on what is the mean and variance of these two random variables. Okay, so these are actually pretty easy to compute. So the expected value, the mean of the sum, is just going to be the expected value of these things. And I know because the expected value is linear that this is just the sum of the individual expected values. Okay, pretty easy. And by the same token, the expected value of the mean is 1 over n times the expected value of the sum, which is then just the average of the expected values. Okay, which kind of stands to reason. How about the variances? Okay, so the variances are a little bit, more tedious, but also not very surprising. So the variance of the sum is basically the expected value of the sum squared minus the expected value of the sum squared, right? We already know this. This is basically going to be the sum of the individual expected values, all squared. What is this? Well, we have to compute this. This is basically like saying, what is the expected value of this times this, right? That's just by definition. Well, one way to think about this is that, for every one of these n squared terms, basically when I have a sum over I and a sum over j of the expected value of xi times xj, which we can recognize actually as the sum of a whole bunch of covariances from what we talked about before. Now, this thing here, I can also think of as the sum over I and j of a bunch of these products of means. Okay, so actually, I guess I misspoke. So this is what we call the correlation. When I subtract off the mean, it's the covariance. So actually what I have here is the sum like this of the expected value of I xi xj minus the expected value of this, like so. And this is actually the definition of the covariance, right? So what I have is, to rewrite the whole thing, I have the variance of the sum is just the sum of the covariances. Okay? And if I wanted to be really proper, I could say, okay, well, it's actually, when j is the same as I, then the covariance of xi with xi is just what we call the variance of xi. And then I could also have, okay, the sum of what's left when j equals 1 to n and j is not equal to I of the covariances, kind of the things that don't match, right? The reason that I put it this way is that in the nice case where, if xi and xj are what we called uncorrelated, that means that the covariance is equal to 0, right? Then the variance of the sum, and this has to be true for all I not equal to j, then the variance of the sum is just the sum of the variances. Okay? So that actually kind of stands to reason, right? And then now I want to talk about is a special case where the xi's all have the same distribution. Okay, so, and there's a special term we give to this. So if all the xi's are what we call IID, and usually you see this in lowercase, and this stands for identically and independently distributed. Or actually, maybe it stands for independently and identically distributed. Doesn't matter. All it means is that distributed. Sorry. All this means is that each of these xi's has the same marginal PDF, and all those are independent, right? So that means that each of these things is just, the same marginal PDF, and they're all independent. So that means that the expected value of xi is just the expected value of x, some x, and the variance of xi, and we can call this mu. The variance of xi is sigma squared for some sigma squared. Okay. So now let's back out what did we learn from before. Well, we showed that in this case, the expected value then of the sum of a bunch of these things is just the sum of these individual expected values. And since all these are the same, we just basically get n times the mean of the variable, the variance of Sn. So we showed earlier that independent implies uncorrelated, right? Or I'm sorry, yeah, independent implies uncorrelated. I almost made a bad error, right? But that's true. So since these things are all uncorrelated, the sum of these things is basically the sum of the variances, and we know that all these guys have the same variance, which is sigma squared. Okay. The interesting part is, what is the expected value of the mean of these IID random variables? Well, it's going to be, the mean is 1 over n times the sum. So that means that no matter what n is, the expected value of the mean is mu, the underlying mean of the PDF, which makes sense. And the interesting part is the variance of the sum is, well, it's 1 over n times the expected. So basically, what I have is this. And let me just make a side note why this is true. Remember that the variance of ax is the same as a squared times the variance of x. That's where this comes from. So that's like saying that my factor here is 1 over n, and so that's where this 1 over n squared comes from, and this is the variance of x. So the important part of this, the implication of this, is that if I have a whole bunch of random variables that all have the same distribution, and I take their average, right, the mean does what I expect, but the exciting part is that the variance, the variance of the mean, sorry for the confusion, as I took the average of this, the variance is going to get smaller and smaller the greater n is, right? So the implication is that the limit as n goes to infinity of the variance of the mean is 0. That means that as I see more and more random variables and take the average, that distribution becomes more and more certain. It converges basically to a delta function around the mean. And so that's good, because in engineering we all the time have a whole bunch of noisy measurements of the same thing. And this is saying that I can kind of average out the noise. If I see lots and lots of measurements and average them together, eventually the noise in that measurement goes to 0, and I can be sure that that average is less noisy than any of the individual measurements. And so that has implications for engineering, and so we're going to talk a little bit more about this in terms of what it means to talk about the laws of large numbers in the next lesson.